And so here it is in its form. Newton's universal law of gravitation. Again, Henry Cavendish determined this. We'll look at his experiment as well and what transpired. How did it work? How did he get this number known as G? He determined it with something called the torsion balance. So we'll look at that experiment. And in the process, he's actually known for weighing the Earth. He's the guy who kind of indirectly determined the mass of the Earth by this experiment. Strange, but you actually can do that because of what Newton developed as the foundation for this type of physical phenomenon, gravitation. So here it is, what's known as Newton's universal law of gravitation. Force of gravity is equal to big G. Now it's really important to write this as a capital G rather than a little g, because little g represents the acceleration due to gravity on Earth, as we know, 9.8 meters per second squared on the surface of the Earth. So big G is a totally different number and is the universal gravitational constant. So that's what it represents here. So this is the gravitational constant. And it's a weird number, but is the one that was developed by this experiment and other ones that followed. So you have G in front of M1, M2, and R squared. Now, after you have this number G, you are able to then calculate using units that we're familiar with. Like, for example, you would expect that the force would be represented in the unit of newtons, and it is with this G. And mass is represented by the unit of kilograms, measured in the unit of kilograms. And the unit of distance here, this radius, the distance between the two objects, is m squared, because it's a squared value over here. All right? And so with this study and the experiment, you determine that G has a specific value. And the reason why it's so important is because it's universal. This value works on Earth, it works in analyzing the planets, it works on galaxies on the level of anywhere in the universe, which is where this idea of, hey, universal comes from, that this idea of gravitation works everywhere, not just here on Earth. And it is 6.67 times 10 to the negative 11th, so it's a very tiny number. Newtons times meter squared over kilogram squared. Well, what happens when you use this constant here is that the kilogram squared cancels out, the meter squared cancels out, and we're left with newtons after using G. That's exactly what we want. This is the current accepted value. Now, other experiments have come along to maybe improve this number to a new decimal place, but this is the one that we'll use, 6.767 times 10 to the negative 11th. Oh, great. So how does this help us answer the question that we were looking for? Well, with this relationship here, we note, though, that gravity is a force of attraction. So it is only attractive. So it's an attractive force. It does not repel. It only brings things together. When we study electrostatics, which is, well, the fancy name for saying static electricity, where you have charges that are positive and negative, you can get repulsion and attraction depending on how you organize the combination of elements of subatomic particles. But in the case of mass, it's always attractive. So that's an important thing to know. All right, so we had our object, our medicine ball, of 6 kilograms, and it has an acceleration of 9.8 meters per second squared with respect to the Earth. Well, guess what that 6 kilograms is? It could be considered mass 1 in this equation over here. G would be a known value thanks to Henry Cavendish, and what we would need next is to figure out, okay, so where's it going? Where is that thing accelerating towards? And it's accelerating towards the center of the Earth, center of our planet. So what's down here as the other object, and not to scale, mind you, but this is our place, the Earth, right? And the Earth is attracting this object here, the medicine ball, and due to Newton's third law of motion, what has to be true is that forces come in pairs. And I know it sounds really absurd, but it's also true that this object is attracting the Earth towards it. Now, it has a different acceleration, but the force is the same. Opposite and equal forces, action, reaction. Okay, this force will be the same, this attractive force, for this object and for the entire Earth. So mass 2 is Earth in this case. And if we knew the mass of the Earth, which Henry Cavendish helped us find, we can look that up now. Well, not right now, but soon in another lesson. The idea, though, that's really important is that the force of gravity here is equal between these. We have our action-reaction pair. Even though it's an invisible force, the 6 kilogram object is attracting the Earth towards it, and the Earth, of course, is attracting the 6 kilogram object towards the center of the Earth. Okay? And this relationship here will tell us about the force. Now, anything on the object of the Earth accelerates at 9.8 meters per second squared. It's not mass dependent. And what we're going to see is why that's the case. It actually comes from here. And what we'll do is we'll look at that case in another lesson. We'll say, why is the acceleration constant for every object? And it comes directly from universal gravitation. The other deal is that, yeah, the Earth is accelerating towards this object, but because the Earth's mass is so huge, if we look at F equals ma, and this ma is huge, that acceleration of the Earth, I mean, the m is huge and the a is barely here at all, the acceleration of the Earth towards this object, the medicine ball, 6 kilograms, is going to be very, very slight, almost not measurable. And you add into the factor that we've got a bunch of other objects on the other side of the world and whatnot, and so the net result is that the Earth doesn't move very much, but it does move, just slightly. Other objects influence the Earth a lot more. We looked at the moon going around the Earth. And the moon, of course, if the Earth tugs on the moon and keep it in, due to the gravitation between them, actually keeping it in orbit, the moon tugs back on the Earth. And what does that do? Well, that creates tidal forces. That creates actually the tide system that we know. It jiggles the Earth and sloshes the water around and creates an odd shape for the Earth because of the fact that there's gravitation between the moon and the Earth as well. And so there are effects. The moon is a much bigger object, even though it's far away. It has a pretty strong effect on the Earth and produces things like tides. So this is really important for bigger objects. But as we'll look and see later, this idea of Newton's universal law of gravitation can extend to something as beautiful as satellites and coming up with geosynchronous orbit and putting a communication satellite up. How fast is going to be whizzing by? What about the International Space Station when we see it above as this beautiful glittering light? So there's a lot of things we can do with it, and so that's what we're going to do during this unit. And I hope you're going to enjoy it. There's a lot of things we're going to talk about. We're also going to talk about how Newton, although this is very powerful, was corrected by another guy you probably heard of by the name of Einstein. So we're going to look at his physics and how it differs from this. Not as mathematical. We're just going to look at it from a conceptual level of, well, what's Einstein's view on this whole thing? How does it differ? And what is the current view of how the universe explains something like gravity? Or how we can explain something of gravity from the universe. That's what it is. This is a lot of talking in this unit, but it's a very rich one with lots of historical figures and whatnot. So I hope you enjoy it when we do it for reals. All right, I'm going to duck and give you a chance to take some notes down. This is what it is. Morad, out.